Good afternoon and most welcome to Chalmers High School or University of Chalmers in Gothenburg, and I'm sitting in the office of Mostad, professor at the university, for an interview, and we are going to talk about Bayesian statistics, which includes the observer, just like quantum physics, one of those most important traits of the Bayesian statistics. Could you give us viewers a short introduction to Bayesian statistics, Petter?
Okay, so it's quite similar to statistics. Well, first of all, statistics is about, the very simple idea of statistics is that it's just summarizing data. But in general, mathematical statistics is more than that. It's more about trying to use models together with data in order to predict things.
Oh, okay.
So that's an important division. First of all, that we are doing more than just summarizing data, basically. And Bayesian statistics is quite similar to classical statistics, except for some technical features and also some philosophical features. And if we focus first then on the philosophical features, you could say that in classical statistics, you build sort of a model for reality that includes some kind of uncertainty, and then variability. You can flip a coin or something, and you can count how many times it turns up heads or tails or whatever, this gives you a kind of probabilistic or stochastic model of reality. So in Bayesian statistics, we do the same, but we also we define what we do as modeling not reality in itself, but somebody's knowledge about reality. And this is an important philosophical distinction, I think, because it means that you really focus on there's not necessarily something true out there. You're just saying that this is the knowledge I have about the world, and then I can make observations, and then I can, in an efficient and logical way, update that information to get a refined model for reality. And this updating is what statistics is about, and this is what we do in Bayesian statistics. Very clearly, we update our models in order to get more refined versions of reality, basically. So that means that in classical statistics, if you for example, let's say, okay, so if I don't know how mathematical this is going to be, but let's say that you flip a coin. So
yes.
So then most people, if it's a fair coin, then you will say that there's a 50% chance of heads or tails.
Yes.
So there's a probability 0.5 of having either one. But it could be that this is a biased coin, so that it's some people who want to cheat or something, they could make the weight a little bit uneven, so that it's more often heads than tails, or the other way around. And if the coin is like that, then you would want to learn how probable it is to get heads by flipping it a number of times and then learning from that sequence.
Oh, yeah.
And this is the kind of learning that is done in statistics, and in frequentist statistics or classical statistics, you would just flip it a number of times, say I don't know, well, 50 or something, and then you would count the number of times it turns out heads.
Yes.
And then you would take that number and divide it by 50, and you would say this is my estimate
Yes.
for the probability of getting heads. And then you would say that in my next throw, the probability of getting heads is equal to that estimate.
Oh.
Now, in Bayesian statistics, we do almost the same thing, but slightly different. We say that there is some kind of uncertainty about the parameter of this model, which is the probability of heads, and then we update our knowledge about that parameter sequentially, so that we get more and more sure about what this predicted next, the probability of heads in the next row is based on all previous observations. So there's not really an estimate anywhere. It's just that you sort of summarize your knowledge about this probability more and more based on the data, so that you in the end get some kind of you can make always a prediction based on all the observations you have done so far. And this is classical in Bayesian statistics, that you take a model for the world, so to speak, your own personal model as an observer, and then you update it with the data you have to make predictions about the new observations. Now, the reason why classical statisticians hate Bayesian statistics is that there is a problem with this, and that is what happens before you have made any throws at all. Right? Now, in classical statistics, you would say that, well, you cannot make a prediction because you have no estimate, right? It's 0 divided by yeah, so 0 divided by 0, so you don't have an estimate, so you cannot make a prediction. Now, in classical statistics, in Bayesian statistics, you always need to have a model that makes it possible to make a prediction, even if you have made no observations. So that would mean that I would say that, well, I must this is the prior knowledge that you have. So I would say that, for example, for this coin, well, this is probably between 40% and 60% of heads, because it's difficult to make a coin that is very, very different than that. So I would say that, well, it's somewhere between that, and that would be my prior knowledge, and then I would update that. So you need to sort of formalize that kind of prior knowledge. So that is something that can be an asset, but it can also be a problem if you feel that this setting of the prior is difficult. Okay, so that was a long introduction to some of the basic ideas of Bayesian statistics.
Why, thank you very much for that. I see some connections already.
Okay.
And you say, what is the knowledge of the observer? And sometimes you can read, what is an observer? And they say, the knowledge in a specific case of the specific circumstance. And then you take away the person, so to speak.
Yeah, exactly.
And you think, well, of course, a lot more knowledge than we usually speak of, but the whole thing. So the knowledge is the person, but just more expensive and much more complicated than we usually think the person is. It's excellent. I see now why Bayesian statistics can be a very good way into quantum mechanics. Because people usually do not see or understand how much inherent information there is in the person. And when they say person, it's like they think about this shallow-minded, just the top part, not the whole constituent details of the whole thing that actually makes what they call in quantum mechanics the superposition collapse. It is not just a narrow ribbon of thinking, it's the whole knowledge, the information, as you say. And I do get that. It's very good. I had to be honest, we were about to ask Peter from the beginning here about topology, but this seems to be an even more promising area for this day's conversation. I think, Kalle, maybe you had a question there as well. Maybe you can just hold it under your mouth.
So it's very interesting, this, and I would like to mention something from quantum physics. You have there something called Pauli effect. That is, the Nobel Prize winner Otto Stern said that this Pauli effect is certain. That is, when Wolfgang Pauli entered into a room that could havoc an experiment. And this Pauli effect it was certain, so to say. When this Nobel Prize winner entered, he was a theoretical physicist and not an experimental physicist. But so in this case, in Wolfgang Pauli, when he was close to an experiment, physical experiment, the technical equipment would havoc. So if we apply this to Bayesian statistics, so let's say I would throw a dice a certain amount of time, how would it, so to say, I would always lose. Let's say I'm a gamer. That would mean if I'm Wolfgang Pauli and I would play the dice, I would always lose. That is the probability. While in classical statistics, you would only count the probabilities that I would lose, or something like that. I don't know if I understood it correctly. Let me give it back to you, Petter.
Yes. Yes, what is the connection? I'm not quite sure if I see the connections as you do, but of course there is a you could say that I mean the connection maybe is the context, that you have some kind of I mean, you would know more about the actual experiment than what is written in the very simple description of it, so that you could have a better model predicting what would happen, because you would have more information about how it would turn out, based on some extra information, and that could go into a prior model for the outcome. However, I would stress that there shouldn't be any kind of magical thing into that one should put into this prior. It's more like in order to be able to deal with this mathematically, you need to have sort of a sensible prior. It needs to sort of summarize what people, sensible people would believe around this outcome, and so yeah, and then if you do that, then you could say that the results are objective, in the sense that if the prior can be considered objective, then this is an objective analysis. But of course, then with this caveat that objectivity is then always relative to this prior knowledge and the modeling of the whole situation.
Oh yeah.
That goes into setting up the predictions that you do. So I'm not sure if if that was an answer to your question, but no. There's another. I'm not sure if you're going to ask about this. But in general, if you allow, I will.
Of course, Peter.
I will.
You're more than welcome.
A little bit, because I'm. We've talked now about the sort of the philosophical connections between Bayesian statistics and quantum physics, but there's also, interestingly enough, a more technical connection.
Oh.
And I'm right now involved with some people who are doing theoretical physics, building these technical prediction models from quantum physics and they're working with the strong force, so quantum color dynamics for this. So they have a quantum theory for the strong force, and unfortunately the theory is there, but it's the mathematics is too difficult to make sensible predictions for things that you want to make predictions for. Things like the radius of the various atoms, or things like that are measurable, but you want to make predictions based on the theory. And then what people do then is that they make an effective field theory, which is taking the Schrödinger equation applied to this particular context, and then they make a simplified theory that is possible to compute with and make predictions. And unfortunately, this field theory or effective field theory will contain some parameters, some unknown parameters, right? Some coefficients, so that you can, you need to plug them in order to get the result. And how big are they? And this is something that can also be answered with Bayesian statistics, and people are using Bayesian statistics in this more technical sense in order to make such predictions and build this theory. So what they're saying is that, well, we have this theory, and it has some unknowns, some basically numbers, like 20 numbers that you need in order to know the value of, and they are sort of then you can say that this is sort of there is some kind of value for them, but you don't know because you don't have the skills to compute them and so on. But then you can use Bayesian statistics in order to learn about those numbers. So then you have a number of experiments. In this case, an experiment is actual measurement of, say, the radius of an atom or something like that, because that is something that is predicted by the theory. And then they say that, well, this actual measurement will give you, or observation will give you an information about the values of these unknown parameters, these things that you want to estimate. And then you can propagate or do the mathematics properly, and then you can learn about these parameters. And then basically, once you have learned about these parameters and know them more certain about those, you can use the theory to make better predictions about new things that you don't know about. Right?
Okay.
So this is always the goal of any kind of statistics, as I mentioned in the beginning, to make predictions.
Indeed.
So I just wanted to mention this without being prompted by a question, because I think it's quite interesting that
it is definitely most interesting.
There is such a connection also.
It brings out memories, and this goes way back. I'm not sure I remember correctly or anything, but some faint memory of equations that needed to be loaded with almost random numbers, and then you can work your way through. And that stuck to my memory. and it sounds a bit similar to what you're mentioning here.
Okay.
You make a model prediction, and once you got it, you can work your way through. Is that somewhat close to what you were saying?
I guess so.
Yeah.
Yes. Yeah.
It makes a lot of sense. It's the working principle in quantum mechanics is tentative in a way,
Yeah.
because it assumes the classical world. And we know it to be wrong, but you need to start with it. And oddly enough, in quantum mechanics, you need to make the conclusions in classical mechanics as well. And the whole experiment is classical. So you load the whole thing with things that you know to be incorrect, but you need them. That pops up many times in quantum mechanics. We have things like imaginary photons. We know they don't exist. We know we invent them, but they are necessary still. So I see a connection. Would you agree with me? Imaginary photons that never existed, never will come into existence, are participatory in what happens in quantum mechanics. Could that be close to these tentative hypothetical things that you load the Bayesian mathematical equations with?
Actually, I don't see it that way.
Okay.
Because for me, when you say that the photon is not real and such things, this is about the translation between the mathematics of how you formulate your theory and the real world, or not the real world, but sort of your everyday world, or the way that you want to formulate things in your brain, basically.
Yes, everyday experience.
So you want to everyday experience. So then you want to have this little ball running around, or moving.
Okay.
Like that. And then the theory doesn't really predict that it exists.
No. They are imaginary.
But something similar exists, and then you try to sort of squeeze it into this thing, so the problem there, I think, is that the mathematics is difficult, and it's very difficult to see how it can, or the connections to everyday observations, and in order to then interpret, in some sense, that mathematical object, you make connections that are only approximately correct, and this is a problem this is a problem. And as a professor in mathematics, I would say that the solution is that everybody learns mathematics, right? but barring that, you have to make some kind of approximation.
Yeah.
Now, I think that this is a different type of approximation than what I'm talking about in Bayesian statistics, because the Bayesian statistics about the uncertainty there is sort of not about interpreting the uncertainty in interpretation of mathematics. It's more an uncertainty in what you can know about I think a closer connection could be like with the Heisenberg uncertainty principle.
Well, it is that one I'm pointing to, actually.
Okay, yeah.
And that's where you have the imaginary photons. Those are the ones that are not observed in the end.
Yeah.
And in mathematics, as the one who informed me said, it doesn't really make a difference. But in your interpretation, from an everyday perspective, you have this weird thing. You say certain things are real and certain things are unreal. When it comes to the mathematics, they keep equal forms. And I was able to understand that because I'm an electronical engineer from the beginning, and all our work was with imaginary numbers. And we asked the teacher, why do you use this? They're not real. That's from our perspective.
Okay. Yes.
And he said directly, they are more real than your world is.
Yeah.
Because they make a difference in the calculation. Whereas your intuitions, they don't make any difference. And this is also very close to a similar speech made by the son of Niels Bohr, the real founder of quantum mechanics, Auger Bohr, and how he was shouting in the lecture hall in Copenhagen that there is no existence. That is an old wives' tale. Don't speak about the atom. My father invented the atom. You would put it into something less if you call it an existence. It's much more complex than that. But it could be that we are on somewhat more equal ground, because you would say the equations give a result, and that's the most important. And you are like a Jesuit. You don't care about the means. You want to get there.
I object to the moral connotations of that.
Well, there is no moral. There's good moral. It's nice to be a Jesuit.
Yeah, well, there's a big jump. Too big jump.
Okay.
Yeah, too big.
We will make you into a Jesuit.
No.
No. Yeah.
Do you mind if I ask a very personal question here?
No.
How do you use that? I know this is secret because this is deep into Chalmers, and you maybe need to shoot me afterwards.
Okay. Yes.
How do you use Bayesian statistics in your line of work here?
No, it's not secret. It's not secret. Well, I mentioned this physics application, but this is not really something I do. I was just mentioning. Another thing that I use Bayesian statistics for is this is much more applied in computations for genetics.
Oh.
So this is just an example. So over many years, I've worked with this problem where you have you can take genetic tests for different people, and then you can, from those, say whether they are related or not, or what kind of relationship they have. Are they brothers or cousins or second cousins, or is it an uncle, or you can do this for a group of persons, and then you can make different kinds of calculations about how probable it is that different pedigrees, as we say, so family trees basically relate these people. So this is something that I've been working on for many years, and an applied research that I'm doing right now. So then this is about modeling the kind of data you have. If you have, I mean, there are the different kinds of uncertainties or variations here. Sometimes you have bad data or very small amounts of DNA, so you have basically very uncertain knowledge about the true genotype or the true genes of that person.
Oh yeah.
And then you have to make probability calculations for this.
I think I even get it. Yes.
Okay. Yes.
Yeah, because you don't know the content of the DNA.
No, so you know. But
and then you put in Bayesian statistics.
So then you put in Bayesian statistics, and the framework is really. I mean, most of the statistics is just statistics and classical or Bayesian, but the framework is really what is more specifically Bayesian, in the sense that we don't ask, what is the relationship between those two persons, because that is a too complex question. What we ask is, how much more probable is the data if they are second cousins compared to if they are unrelated? And this is and from that, you can also say that, well, do you have any other data telling you whether they are unrelated or second cousins? And then you can combine that knowledge, because then that knowledge is like the prior that we talked about,
Yes,
the other contextual knowledge. You combine that with the computations from the DNA data to tell you, well, given all of this, given the contextual knowledge about how the hell did you get to make this test,
yes,
and the DNA tests, then from that you can compute, well, this is like 99% sure that they are in fact second cousins from this data. So that's just this is one of the things that I'm working on.
I think that was really helpful. I hope it's for the viewers too, because now I understood better what Bayesian statistics are.
Mm.
It is like taking different uncertainties and combining them.
Exactly.
You're
onto the right track now. Yes.
Oh, thank God I asked you about your work. Yeah. And well, I didn't know you were working for the dog food industry. Pedigree is paying your salary, I imagine. No.
The pedigree simply means family tree.
Okay.
Yeah, it's a technical term, just because. Yeah.
Wow. Wow. I need to open up this Pandora's box of Bayesian statistics.
Mm-hmm.
I've been waiting too long to get into it.
Mm.
But I now see what is this real-time understanding. I now see how it relates to quantum mechanics.
Okay.
So that's just great, Petter. Thank you for that. Mm-hmm. Maybe some finishing words about Bayesian statistics, why you like it, or were you forced by the pedigree company to do it?
No. I think my actual background is in pure mathematics. And I personally actually have a PhD in pure mathematics. Ooh. And I didn't start to study statistics after I had completed that and done some doing research in different ways. And with that background, I think I have in common with some other people who are interested in Bayesian statistics that this is a more mathematical way to relate to statistics. Because if any viewers have done any statistics, classical statistics, you will often notice that it's a little bit ad hoc. Mm-hmm. You say that, well, you have this data and then you use, it is recommended that you use this one, and then you have to use this p value of 0.05, and then because this is what people do, and you have all of these a little bit ad hoc and things that seem to come from nowhere. Just and as a mathematician, I didn't like that. So in Bayesian statistics, in some sense, paradoxically, it's more objective.
Yes.
Because you specify exactly how you do the calculations, mm-hmm. and you specify that you get your model from your context. Of course, that depends then on the context, and there is some kind of subjectivity mm-hmm. in the way that the observer or the person making the model creates that model, but that is out in the open.
Yeah,
right. Yeah. It's specifically specified how you make your model, and once you have a model, the rest is mathematics. Mm. So that's what attracted me to Bayesian statistics, I think.
Oh, I can see the connection now. Hmm? That made it very clear.
Good.
Well, I say thank you very much, Petter. That was excellent.
Thank you.
Great privilege to having interviewed about Bayesian statistics, which I now will commence.
Okay.
Fantastic. And thank you very much for listening in, and have a very pleasant afternoon.
You too.
Thank you.